So, today we welcome our first Zurich Financial Services Distinguished Visitor, that's ZFSDV, for 2018, Dr. Gavin Schmidt, the Director of NASA's Goddard Institute for Space Studies. So, first a little bit about ZFSDV. Dr. Schmidt, you are now entitled to append these initials to your Who's Who entry. It goes after the PhD. ZFSDVs are supported thanks to a generous gift from the Zurich Insurance Group for a short-term residency at the Bren School. During this, they can teach short courses, they can conduct seminars, they can lead colloquia on their research and professional endeavors. It's also become traditional, realize anything that goes for more 2 consecutive years is traditional in California. It's become traditional for ZFSDVs during their residency to deliver a lecture aimed at the broader community, both broader Bren School and university community, furthering the university's goal of addressing critical issues of the day and inspiring all of us towards their possible solutions. So, Dr. Schmidt might be an archetype for a ZFSDV. Kind of rolls off the tongue, doesn't it? He's an eminent climate scientist with over 120 publications. He directs one of the world's most influential climate research organizations. So by a purely academic reckoning, he's at the top of his game. But Dr. Schmidt is also a skilled and passionate science communicator. If you visit his homepage, what you'll find most prominently featured are among his works are videos, slides, and articles explaining climate change and climate science to general audiences. Don't worry, you can find those 120 plus publications by drilling down. One of those presentations is a TED Talk, of which I was the 1,166,109th viewer. So, not Beyonce yet, but getting there. We all get that making environmental research and information more broadly accessible is one of the things that is the greatest challenges facing us as environmental professionals. And we're very pleased to have Dr. Schmidt help show us how it's done. So, no pressure. Today, Dr. Schmidt will tell us about climate models, the most critical and probably the most misunderstood tools in our attempts to understand climate change. He asks, what are they good for? So let's find out. Dr. Schmidt.
Thank you very much. Thank you very much for such a warm welcome and for hosting me here this week. It's been great so far. Unfortunately, the day I got here, I came down with a cold, and I have been sick as a dog since Monday. So if I appear to be speaking slowly and deliberately, it's not because I'm thinking very deeply or that I'm very intelligent. It's just that I actually can't get the words out fast enough. But feel free to think about how that actually works. I'm going to talk about climate models. Here's an animation of a cloud. This is water vapor in a simulation, relatively high resolution, I think about 10-kilometer resolution. And you can see a lot of very interesting effects. There's a number of atmospheric rivers, which are a phenomena you may be aware of in this part of the world. There's some cyclones that occur. There's some storm features. There's a lot of interesting things. So how does this come about? Right? What goes into these models? How useful are they? Are they just useful for making pretty animations, or are they actually of practical significance? I don't need to tell you that the climate is changing. We can go pretty much anywhere where there's ice, and places where there were ice recorded, this is in the 19th century. You can go back to these same places right now and retake these photographs, and you can see how things have changed. That's in the Canadian Rockies. No, the Alaskan Rockies. But I can go to the Rockies, I can go to the Andes, I can go to the Himalayas, the Alps, glaciers in Africa, glaciers in Papua New Guinea. Did anyone know that there were glaciers in Papua New Guinea? Well, not for much longer. You can go anywhere and you'll see the evidence of change. The elements of the system that have a long-term memory are showing these changes very, very clearly. Places like Alaska, where people built, unfortunately, villages on sand. Now, the sand that they originally built it on was frozen, and now it is not. And erosional rates, because of the lack of sea ice in this region, this is just off the Bering Sea, are such that the erosion of this coastline is tens of meters per year. Okay. This house obviously no longer exists. I don't need to explain to you that sea level is rising. Places like Miami are seeing increasing amounts of what is called nuisance flooding. But basically, it's the ocean telling them that they're not really supposed to be living there anymore. We can put together all of the instrumental data, going back at least to the mid-19th century, and get estimates in a quantitative sense of how the climate has changed on a global scale since the 19th century. And these are four relatively independent methods for pulling that together. And you can see that while there's a lot of ups and downs associated with El Nino events and volcanoes and the like, there's been a long-term trend that culminated in 2016 with the warmest year in the instrumental record, which beat out 2015, which had been the warmest year in the instrumental record, which beat out 2014, which was the warmest year in the instrumental record. You'll be pleased to know that 2017 it will only be the second warmest year on the record. One of the interesting things about this whole story is that back in 1988, when my ex-boss and the person that had my job before I got it, Jim Hansen, he gave some pretty impressive testimony in Congress, and he said, global warming is here, we can detect it. And he said that in 1988, in June 1988. 1988 was also the warmest year on record. Now, it is not even in the top 20. Things are changing. But how big a change is this really? Is it something that we can detect and measure and be confident that we've seen something? But is it actually something that makes a difference to anybody? And so you have to have some kind of context for what are the magnitudes of change that you expect in the global mean temperature, right? You know, this is just over 1 degree Celsius. It's around 2 degrees Fahrenheit. Is that a big number? You know, the temperature in this room is going to go up by 1 or 2 degrees Fahrenheit just from us sitting in here and all gathered around. And yet none of you are going to go extinct and the chairs aren't going to melt, right? So is this a big number? Is it worth even paying attention to? That's where understanding a little bit about paleoclimate comes in handy. We can go back, say, 20,000 years, and that was the peak of the last glacial maximum. Massive ice sheets over North America and Europe. So much water in those ice sheets that the sea level had dropped about 120 meters. Where there is boreal forest now, there was just ice sheets and tundra. And those ice sheets went all the way down to New York City from the Arctic Circle. How much colder was the Ice Age than the pre-industrial? I'm sorry? Sorry. So how much colder was it? The answer is not that much colder. It was about 4 to 5 degrees colder Celsius. So when you've got just over 1 degree Celsius here, this is not just a small number. It's about a quarter of an Ice Age unit. And you think about how different the Ice Age was in terms of ecosystems, sea level, climate. This is a big deal for the planet. I made this. I just like using it. So it's how each month's temperature over a climatological period has changed over that time. So the blue is in the 19th century, and the red is the last 10 years. And you can see that the changes in climate, what was a normal January 100 years ago almost never happens anymore. Right? And if you put this on an absolute scale, you'd see that Januaries in the 19th century are as warm now as Marches used to be. How do we interpret all of this? How do we understand all of this? Well, we first have to understand that the challenge to understand the climate system is enormously hard. It's an enormous challenge. You have to worry about things as small as the micron scale for little particles that nucleate cloud droplets. And of course, you have to go all the way up to the planet, right? That's 14 orders of magnitude. In time as well, you have to worry about things happening at the microsecond level all the way out to millennia. Again, about 14 orders of magnitude. There's no single physical theory that works equally well across such a large range. And so we have to be both aware that this is a very difficult problem. We have to be aware that it's a very difficult problem. What do? Well, we use computer models. Now, some of you might recognize this. A few of you. This is a punch card. It's one line of Fortran code that was part of the GIS climate model back in the early 80s. Luckily, we no longer use punch cards, but we still use Fortran, interestingly enough. But I'm pretty sure that this particular line is no longer in the code, thankfully. So, remember those 14 orders of magnitude. Let's think about weather models for a second. How does that work, right? So, weather models, you try and resolve as much as you can, and that's a function of how fast your computer is, right? So, weather models, they'll resolve things from, maybe the 50-kilometer range all the way up to the global scale, and they'll be run for, every 15 minutes out to a few weeks, maybe a few months. Okay, what we call those scales are what we call the resolved physics, the kind of things that we think that we're doing a pretty good job at calculating based on first principles. Conservation of energy, Navier-Stokes equations, and the like. But of course, there's all the things that are happening at the smaller scales and faster than we can resolve. Right? So we call these subscale processes, and these are the things that need to be parameterized. These are the things that need to be approximated. And this is where all of the art goes into climate modeling. These things are difficult, right? Because you're making approximations and you're trying to integrate over very heterogeneous situations, whether it's a cloud field or a landscape or an ocean eddy. Back in the 1990s, the scales that were resolved by climate models were actually quite small, right? So obviously you want to take it out a few hundred years, but you weren't getting the same resolution that even the weather models were getting. Nowadays, it's a little bit better. This would be equivalent to what was in the CMIP5 archive, and so we're just about to start CMIP6, which is the new coupled model intercomparison project, which you don't really care about, but we spend a lot of time working on. And the interesting thing is that we're basically increasing the order of magnitude of our resolved physics by about 1 order of magnitude every 10 years. So that means that if I want to do a calculation for 2100 based on a fully first principle, everything included climate model, I basically have to wait until 2100 before that will be possible. I don't want to wait that long. So, for my entire career and for decades to come, we always are going to have to deal with the fact that models have these two components. One part, which is well resolved, and then the important stuff, which is not. How do we go about building one of these models? Well, basically, we just go to all the different places in the planet where something interesting is going on, and we try and work out what processes are happening and what the rates of change of those processes are. And we're going to build a jigsaw, right? So each set of processes is one piece of that jigsaw puzzle. Slight aside. So when you do a TED talk, you're not allowed to use anything that anybody else has used, right? You can't use anything that somebody else has copyright on. Everything has to be public domain. You have to make your own. Okay, so I thought, well, I'll go with the whole jigsaw thing. And then, but I couldn't use somebody else's jigsaw outline that they'd already made for PowerPoint. I had to make my own, which is why it's a little bit like kind of wonky in the corners. Anyway, moving right along. So this is actually a picture. I'll try not to amuse myself because that's just going to cause me to cough. This is a picture of sea ice from a plane flying over the Arctic in the summertime. These are ice floes, and then the dark patches in between are leads, which is open water. Temperature here would be around 0 degrees Celsius. But we can go down there, we can plonk scientists on one of these ice floes for years at a time and have them measure everything that they can measure. How reflective the ice is, how quickly it forms, how quickly it melts, the density, how much salt there is in it, what the fluxes are at the base of the sea ice, what the fluxes are at the top of the sea ice. And we can encapsulate that in code. And that's one part of the jigsaw. We can do the same thing for clouds. We fly into clouds, on top of clouds, underneath clouds, and we try and work out how long do clouds last, when do they form, how do they dissipate, what happens when they rain. And again, that's one extra piece of that jigsaw. The same thing for the sun's radiation coming from the top of the atmosphere down to the surface and then back up again, how it gets absorbed, transmitted, scattered through the atmosphere. Each of these pieces is one more element that we can kind of put together somewhat independently. The impacts of the ocean, the winds, etc., the impacts of plants and trees for cycling of water and changing the albedo of the planet, etc. Now, the point here is not that we know everything. We don't. There are still big gaps in our understanding. But when you put all of these pieces together, you can recognize what planet you are on. Climate models go back at least to the 1950s, 1960s. The first atmospheric model was by a chap called Norman Phillips, who's still alive, interestingly enough. I think he's in his 90s now. Lives in New Hampshire. Manabe, Hansen were pioneers here. Kirk Bryan was a pioneer in the ocean. Hibbler, a pioneer in sea ice. The upper atmosphere stuff was generated by people who were first concerned about the SST transports, supersonic transports, and then the ozone hole and other stratospheric processes. But one of the things that's been very interesting is that if you go back to the 1970s, all of these things were independent lines of research. The sea ice people didn't talk to the atmosphere people, didn't talk to the ocean people, and they worked on their own problems. What the most exciting thing about modeling that's happened in the last 10 years is a little bit like the Borg. Climate models have kind of assimilated everything. And that allows you to do all of the things that you were able to do back here in the 1970s with better precision and with higher details and things, but also really to look at how all these things interact in ways that we really weren't able to do even 20 years ago. So, the first thing you have to remember about models is that they're all wrong. Right? Our models are incomplete. They have approximations that are not correct. And with general circulation models, you can see the wrongness of these models just by drilling down. You get away from the global mean, you drill down to some regional thing, and you'll see that the rainfall pattern doesn't quite look like the rainfall pattern, the winds don't quite look like the winds. From 10,000 feet, it looks pretty good. But if you get down to the nitty-gritty, it doesn't. And so, all models are wrong, and that's true for all models. It's true for quantum mechanics, it's true for general relativity. They're all wrong in some sense. But with complex simulations like this, it's actually easier to see. And yet, this is a simulation. 1 year of reanalysis using one of the NASA reanalysis models. What you're seeing here are different particles in the atmosphere. So the orange particles, that's dust coming off the Sahara. The blue swirling, that's sea salt being lifted by the winds. The white wispy stuff is sulfate pollution emitted by the burning of dirty coal. You can see a lot more of that in China. You can see all this green stuff here coming out of Indonesia. Each of these red dots is a fire that has been observed by satellite, and then we estimate what those fires are putting into the atmosphere. And you can see here some cyclones. You can see a big signature of the sea salt. What you're looking at is all the different components of the climate system being moved around by the dynamic patterns of weather, the storms, the winds, etc. But each of these components, the sea salt, organic carbon, dust, they impact the climate themselves because they're interfering with how solar radiation and long-wave radiation is being transmitted through the column. So you have a very complex dance where all of these things are being impacted by the weather and then in turn impacting the weather. And that's a volcano that just went off just north of Madagascar. It was a small volcano. So. I can watch this for hours. There's a lot of different stories here. There are, you can see these plumes of Saharan dust, sometimes reaching up to Greenland. You can see smoke from fires in the US making their way across to Europe, and pollution from China making their way to California. So, if the models are all wrong, how do I tell whether they're useful? Right? So this is the question that you should be asking. Are these models useful? And so there, the notion of skill is very useful. Right? So how do I define skill? A model is skillful if it makes a prediction that I wouldn't have been able to get otherwise, that actually turns out to be more correct than anything I would have had otherwise. And so with weather forecast models, it's pretty easy to see, right? So does your weather forecast beat the notion of persistence, right? So if the weather today, I can say, well, maybe the weather tomorrow is going to be very much like the weather today. And most of the time, that's a pretty good estimate. But when it's wrong, it can be a very big deal. And so we had a situation here last week where it's certainly the weather one day was certainly not like the weather the previous day, and yet it was very well forecast. Right? That forecast was skillful, right? Because it told you something you wouldn't have been able to get otherwise. Now, with weather forecasts, you can test that skill every day for decades. You're making a forecast, you check it. Make a forecast, you check it. Make a forecast, you check it. And that allows weather forecasts to get better pretty much continuously over the last 30 years. So now 5 and 7 day forecasts are as good as 3 day forecasts were 30 years ago. Right? That's a very impressive improvement in skill. But how do I evaluate the skill of a climate model? Well, we're looking at climate changes. So what are the things that have caused the climate to change in the past? What elements of the climate have been kicked by asteroids and the like, where we can have an estimate of what changed and what the response was? So we know, for instance, that over the last 2.5 million years, wobbles in the Earth's orbit have paced the ice age cycles over the whole of the Quaternary. Right? So we know that that can be a really big driver of climate change. We know that the sun has a quasi 11-year cycle in sunspots and activity, and perhaps quasi-centennial variability as well. We know that volcanoes impact the climate on very long time scales. They provide the carbon dioxide that balances the long-term carbon cycle, but on short time scales, they put enough stuff into the atmosphere and sometimes into the stratosphere that they will cool the climate for a few years, depending on how big they are. So we know that that happens. We know that smoke and fire affect the climate. We know that the ozone hole has affected the climate. We know that deforestation has affected the climate. We know that contrails are affecting the climate. And of course, we know that greenhouse gases are affecting the climate. So how do I judge whether the models are skillful? So I'll walk you through one example. So in 1991, a very big volcano went off, Mount Pinatubo, put a huge amount of sulfur into the stratosphere and caused, as you can see here, a big increase in aerosols in the stratosphere. It started off in 91 and kind of peaked in 92, kind of decaying 93, 94. Because these aerosols are effectively white, they're reflective, and so they reduce the amount of solar radiation coming into the climate system. And so you get a radiation imbalance that's tied very closely to the aerosol depth. That kind of peaked around 1992, and that changed the radiation balance by about 3 watts per meter squared. That's a pretty big deal. As you might imagine, if I reduce the amount of sun coming in, the planet is going to cool, and indeed it did. And so these are 2 estimates of how much the planet cooled, and then the light lines underneath it are model estimates of what that cooling was predicted to be. Now, interestingly enough, when this went off in June 1991, people had a very good sense of how much sulfates had been put into the atmosphere quite quickly. And by October 1991, people had actually made predictions of how much cooler it would be for the next few years. And those predictions made with what were then state-of-the-art models, but are now not very good models, were spot on. But it doesn't just work on the global scale. It also works where you've got dynamics, where you've got things that are going on. One of the things that you see after lots of big tropical eruptions is that in the winter after that tropical eruption, there's actually a warm pattern in Europe associated with it. And you've got a kind of warm, cold, warm pattern that goes across the Europe. And that's associated with changes in the wind patterns, right? Because the temperatures in the stratosphere have changed, that changes the winds, and that changes the amount of heat that's being advected around. And the models produce that same thing as well, right? So we can go in, we can test these things, sometimes even ahead of time, make predictions for what impacts we expect to see, and then see whether they actually come true. So models are skillful in response to volcanic eruptions. Here's an estimate of what's been going on over the 20th century. These are the observations. It's been slightly smoothed, I think with a 5-year filter, so you're not seeing too much weather. The blue and the yellow, that's just weather. That's not predictable ahead of time. So that's uncorrelated in the models and in the observations. But as you get towards the end of the 20th century and the beginning of the 21st century, you see something else emerge. You see something else emerge that is not related to the weather, that is not related to that internal variability, and in fact is a signature of the climate changes that we've seen. And the model does a pretty good job as well. You see more warming over the land than the ocean. You see the most amount of warming in the Arctic, and you see the least amount of warming in the Antarctic. There's a pretty good pattern. Excuse me. But why did it do that? And this is where models really come into their own. Because the models, you can do lots of counterfactuals. Right? You can say, well, what if only that one thing happened? The orbit changed. Turns out that doesn't make any difference over a short time period. The sun, very small impact on the surface plateau. Volcanoes, they do make a difference to the climate. And those are all natural phenomena. So you can say, I should put in a pause there, hold on. Whoop. Oh, no, go back. You can't quite see it, but there's an error bar here that is a measure of the weather variability. Okay. Now, if you just include natural factors, you can't get a pattern that looks like the observed change. And in fact, if you calculate the uncertainty there, this is about a 2 sigma variance in what you would expect just based on weather. This is actually a 5 sigma outlier. So if any of you see particle fever about the Large Hadron Collider and the discovery of the Higgs boson, that was their test. Did they find a signal that was different enough from their background model at 5 sigma before they could say, oh yes, that we found something new. Our ability to detect something new is at the same level, right? So if you don't include any anthropogenic effects, you have a 5 sigma problem to deal with. And 5 sigma almost never happens, right? Unless your underlying model is wrong. So let's throw in some of those anthropogenic effects. Land use and land cover change, that cooled the climate a little bit. Ozone pollution has warmed the climate a little bit, particularly near the surface. Aerosols, sulfates, nitrates, organic has cooled the planet. But of course, greenhouse gases have actually warmed the planet more than we would have actually than we've actually seen if they were the only thing that was going on. And so when you put together all of the anthropogenic changes, you actually end up with a pretty good match to what's been going on. And of course, if you include the natural and the anthropogenic changes, you end up with a pretty good estimate of what's been going on. Oh, no, hold on. But the key reason why we use models follows from this. If we had observations of the future, obviously we would trust them more than models. But unfortunately, observations of the future are not available at this time. So this is why we need to study models, and we need to assess when they are skillful, how they are skillful, and when they're not. But it's a real challenge, and you have to pull together things that happened 8,000 years ago. There was a massive lake burst. Lake Agassiz collapsed around 8,000 years ago, dumped a huge amount of fresh water into the North Atlantic. We can test that, and we can put it into our coupled models, and we can see how the models respond. And we can see whether they match the changes that we've seen in the Greenland ice sheet, or in caves in Europe, or in ocean sediments off Norway. And that allows us to test how skillful the models are. And those are the same models that we're using to make those predictions of the future. We have to be looking at things that are outside of our 20th century sample, because we haven't actually seen that much yet. And the predictions that we're making, and I'll show you some of those in a second, are way outside the bounds of what we can calibrate just by looking at the 20th century. But we've been doing this model business for a while, right? So how have we been doing? So in 1981, this was an estimate of what was going to happen. It wasn't a GCM. It was just a simple model that people estimated what was going to happen, and they did a pretty good job. It's actually warmed slightly more than they anticipated. The first transient GCM result was published in 1988, but it was actually done in 1984. And the coloured lines are three different scenarios going forward into the future. And this is the forecast, and this is a real forecast. Right? So, and then this is the actual temperature change that we saw. Not too bad. One of the first CMIP exercises, CMIP 3. Now you can see that we're getting better, right? We're getting better at filling in some of that uncertainty. So there's no weather uncertainty in any of these runs. But here we're doing multiple ensemble members, multiple initial conditions. And so we have a bigger spread and a more coherent spread. And again, this is what's actually been observed, and this is the prediction of the models. And we did the same thing in 2005, and we're just about to do the same thing again. And again, we're doing pretty well. So when people tell you that models don't make good predictions, that's not true. They do make good predictions, but not for everything. So, what's going to happen? Now, these are three different scenarios going forward into the future. This business as usual is more like a burn it all scenario. Burn it all the oil sands and the tar shales and the natural gas and the methane hydrates and the coal and everything. Just burn it all. Aggressive mitigation would be cuts in emissions that would be compatible with the Paris target of 2 degrees warming by the end. Steve Schneider once said that the least likely outcomes were everything's going to be fine or it's going to be the end of the world. These kind of span that. This is our scope. What we do, what we choose to do as a society, what we choose to do economically, technologically, puts us somewhere in the middle, hopefully. I don't think we're going to do this, my personal opinion. I sure as heck hope that we aren't going to do this. So we're going to do something like this. But what does that mean? These temperatures here, 4 or 5 degrees warming in the Arctic, incompatible with summer sea ice. What's the long-term sea level associated with that? Meters of sea level rise. How fast would that occur? We're still not at the point where we can say that very clearly. Changes in temperature in the US, 3, 4, 5 degrees. That's like a shift of 1,000, 2,000 miles in kind of climate zone, moving kind of Chicago to Oklahoma. Those are very different places. These changes, the warming here, incompatible with almost any sea ice. And look at the warming over Greenland, Antarctica. This sets us up for a sea level rise of multiple meters over a certain amount of time, but a very big deal. I'm contractually obliged to include a picture of a polar bear in all the talks I give. And I don't mind doing so. I took this photograph and I wasn't quite as close as it makes it look. That's not love in its eyes, that's hunger. They are very cute. And we spend a lot of time worrying about polar bears, and I think rightly so. They will be increasingly in trouble. But we don't spend as much time worrying about less photogenic creatures. So some of you will know what these are. These are mountain pine bark beetles. And they have a very interesting climate dependence. To survive the winter, they produce antifreeze in about a 6-week period towards the beginning of the winter. And if it gets cold during that period, if it gets cold enough during that period, then the whole thing just stops and they die, and you kind of slow down the breeding cycle. But if it doesn't get cold enough, then they survive in large numbers to the next spring when they pop out again and do untold damage. And of course it hasn't been getting that cold. And so we've been seeing massive outbreaks of pine bark beetles all the way up through from Colorado to British Columbia and to Alaska. Multiple species, all of which are basically responding in a very similar way. Go back to this lady. I end with this because we don't really care very much about the beetles, and we don't really care very much about the polar bears, but we really, really should care about people. And people, when you end up in a situation where you don't have options, where your city is flooding, where your city is burning, these are real people that are involved. And this is why we care. The issue. I don't work on climate models because they're neat, because they're complicated, because they involve coding. I mean, obviously, I like all of those things. But I work on them because they help us answer questions that people need answered. And they're not perfect. They're not perfect answers. But they are things that people need. And as I've moved from being a mathematician to working on simple models to working on complex models, I've been driven by this need to answer questions that are more and more relevant to more and more people. Let's get that. Sherwood Rowland, who won the Nobel Prize for chemistry for working out the reactions that led to ozone depletion in 1974. He said many years later, "What's the use of having developed a science well enough to make predictions if, in the end, all we're willing to do is sit around and wait for them to come true?" I find this every year. You know, last year I predicted, back in January, that 2016 would be the warmest year on record. I predicted that 2017, a year ago, would be the second warmest on record. My scientist hat, when I'm wearing my scientist hat, I think, ooh, how clever am I? I've taken something from nature. I've understood something about the system works. I've made a successful prediction. Look how clever we are. And then my citizen hat, when I'm wearing my citizen hat, I go, oh my gosh, I don't want these predictions to come true. And so we're stuck. We're stuck making predictions that we don't want to come true. And that's tough. And we have to do more to get around that. You know, it's not enough for us to just be content to make predictions. We have to do more. We have to engage with people. We have to help people find solutions. We have to help people make better policies. And obviously that can be difficult at times, depending on the way the winds are blowing in Washington, D.C. But Washington, D.C. is not the only place in the world. And there are great initiatives and good people working to do something to avoid that business as usual scenario all over the world, including here at the Bren School. And so I'm very glad that I had a chance to talk to you, and I will be happy to entertain any questions.
Thanks very much for your talk, Gavin. I know it's tough when you're sick. I wanted to ask you a question about extreme events and attribution, because with what's happened here in California, as you know, we've had multi-year droughts, we've had heat waves, we've had fires, we've had extreme precipitation just the other day. And people always ask me, well, is it due to global warming? And I say, well, you know, there's a complex series of studies that have to be done. You can make a causal chain, but it's not easy to make that attribution. How would you answer that question?
So, you're correct. It's not easy to make that attribution. There are some things that are increasingly easy, right? But you have to think about, right? These are extreme events. So, to characterize what happens at the tail of a distribution, you need a lot of information. You need a lot of data. We don't have enough data in the observations for a lot of these events, right? So we can't just like kind of see how those things have been changing over the last 1,000 years to say what the attribution is. So how are people doing this? Instead, they're using models. They're using weather models and they're using climate models. And the idea is that you run them a lot of times with climate change, without climate change, and you see and you try and characterize those tail of the distributions. Now, for that to be credible, you have to have models that include these phenomena. Right? So right now, we don't have models that include tropical cyclones to that level of detail that we can run hundreds of times to get those statistics. Right? In about 10 years' time, we will, but right now we don't. So the attribution of extreme events that's happened so far, they're mostly associated with synoptic scale events that we feel that the models do a better job of. So you can you can look at the distribution of these big synoptic events, and you can compare that to the observations. You can convince yourself that the models are doing it correctly, do with and without climate change, and you can see a change. Now, what happens is that some of those changes are very sensitive to exactly what model you looked at, right? So things that depend very delicately on exactly where the winds are going, those are the things where it's not at all clear. So track changes of storm systems, right? Those are hard to be able to say anything very much about. But things that are more tied to the thermodynamics, right? So intensity of precipitation, heat waves, those kinds of things are in fact well characterized and robust across multiple different kinds of models. And what we'll see over the next decade is more and more extreme events kind of coming into the envelope of things we feel that we incredibly say something about. And we will then have like a library, if you like, of model simulations that we can just kind of drop in and make a kind of very quick attribution whenever we see something interesting, right? We won't have to do it specially for every single new event. We have to set up some whole new set of simulations. What we'll do is we'll create a library of thousands of simulations that include this physics, and then we're just going to come in and say, boom, this kind of phenomena, this kind of threshold, how often is it being taken, how often is it being exceeded, how often does it happen, and what's going to happen? And the answer is not always that climate change is going to make it worse, right? I mean, sometimes cold snaps. I know it's been cold on the East Coast when we left, but in fact that happens less now than it used to happen. But I think we're just getting a little soft. Not as soft as you guys, but still.
Hi, thank you for your talk. I know you're very sick. Hopefully this is an easy question to answer. So logistically, with the models that NASA and NCAR and NOAA produce, because I hear them all talk about climate models, do they all culminate at NASA? Is everyone producing separate climate models? Like how much interaction is it between like those different entities?
So we interact, but they're mostly independent efforts. It's not necessarily the way that you might have designed this system, but the fact is that the NASA models are funded by a different mechanism than the NOAA models, than the NCAR models. And everybody wants their model to be the best. Now, what we've learned is that it's important to maintain a diversity of models so that we get to sample the structural uncertainty in models. And so people are now no longer claiming that we should just have one model that's the best model, but that we just need to have a better idea of, we should have better controlled ensembles of that structural uncertainty. And so when different groups do things independently, they make different errors, they make different assumptions, they include different physics, they have slightly different views on what's important or how they tune the model. And it's important to maintain that to get a sense of how robust any particular attribution or prediction is.
My question is about the geoengineering, and I think many of us are thinking geoengineering as a kind of final emergency ejection button, and how the effect of geoengineering, like for example, artificial cloud formation or ion fertilization, are incorporated into climate models in current state.
So you can put all of these things, you can simulate these things. It's a little bit hard to get funding to do any of those things for some reason. The geoengineering that is the most studied and cheapest in some sense, is the addition of sulfate aerosols into the stratosphere to emulate, Pinatubo, on a much more frequent basis. The science of that is interesting. There are interesting feedbacks that you get on ozone, on tropical rainfall, on high cirrus clouds. I mean, they're interesting things to look at. And there's a whole group of people who are looking at that kind of thing, though generally speaking without any funding. But the key issue with geoengineering is it's not a scientific issue. It's a legal issue, it's an ethical issue, and it's a moral issue. And the reason why geoengineering won't ever exist and be sustained is because of all those things. It's got nothing to do with the science. And so if we think that we should study the science of geoengineering because that's going to help us out, that isn't going to help us out. It's the legal and international framework for allowing geoengineering that will prevent it from happening or being sustained. So there's a great book on this called Fixing the Sky by Jim Fleming, who's used to be an atmospheric scientist and now is a historian. And he goes back through the history of weather modification. And all of the issues that people are talking about with geoengineering have been dealt with, when people were trying to do cloud seeding or people were trying to prevent hurricanes from forming. And all of these ethical issues, liability issues, they've all been worked out. And in fact, people don't tend to do those things anymore because they couldn't find a mechanism that allowed that to work properly. So people still pay for cloud seeding, but it's just, Aspen pays for cloud seeding so they can have snow, but they have no idea whether it works. Texas pays for cloud seeding to bring rain. They have no idea if it works. I'm good.
Thank you very much for
Thank you.
the presentation.